Okay everybody, welcome back. So this tutorial is going to go through steps in doing a simple regression in SPSS and getting some of those values in R and JASP and Excel even. So let's get right into doing regression in SPSS. So here we go, we've got our data file that we had previously opened to look at correlations. In fact, it's just called correlation.sav. And what we're doing is we're looking at height and shoe size, and we've also got sex in there. But what if we want to predict a person's shoe size based on their height? We're going to use a regression analysis, a simple regression. And the way we do that is simply going up to the Analyze tab, and we're going to select Regression, which is right under Correlate. And then we're going to move over and we're going to select Linear Regression. Gives us a few options here. So the first is our dependent, and that is what we want to predict. So I'm going to say I want to predict height, and I'm going to base it on shoe size. Now I'm just going to go through my different options on the side here. So statistics, it's going to give me estimates, model fit. We won't worry about these things for now. Okay, plots. I'm not going to worry, you know, we can have a look at what these mean later. And options. So use probability of F, include constant equation, I'm good. So all of these things I'm just going to leave the way they are. So I'm going to click on OK and see the output that I get. So what we see is we've got a model summary, and this gives us an overall R value, which is 0.899 and R square of 0.808. And note that this is the same thing as we got in our correlation analysis in terms of our R value. And this is because it's really the same thing. The only difference with the regression is it gives us an intercept value. It's a second beta coefficient that allows us then to know where that sits on the scale and then to predict future values based on that. So if we scroll down, we see our coefficients, and these are our two beta coefficients. The first one that says constant is our intercept. So this would be our height if our shoe size was 0, which of course is not going to ever be the case, but this is height in inches if our shoe size was 0. And then shoe, as shoe size increases by 1, height increases by 1.9 inches. That's basically what it means. Now, the next thing we may want to look at is whether or not this is significant in terms of the regression equation being significantly different than 0. And what we see is that we end up with a F ratio of 83.955, and its significance is less than 0.001. The way we calculate the F ratio is simply from the mean square divided by the residuals. So 149.381 divided by 1.779 gives us our F ratio of 83.955. Okay, quite simple. So let's see how we can approximate this sort of thing in Excel. So if I'm going to open up Excel, and this is the file we had used for looking at our correlations previously. So if I go up to Data and over to Data Analysis, I can select Regression. So for my input Y range, I'm going to select height. And for my X range, I'm going to select shoe size here. And I'm just going to hit OK on the output. And what we see is the output is very similar to what we just saw in SPSS. So our R value is 0.8986, our R squared value is 0.807, and our NOVA gives us the same output. So an F value, which is based on our mean squared divided by the residuals, right? If I just did equals this divided by this value, we'll see we get 83.9495. And its significance value is 1.35 times 10 to the negative 8. Again, it gives us our beta coefficients as well, which means that at a shoe size of 0, our height would be predicted to be 50 inches. And with each increase in shoe size, our height would increase by 1.91. Now, another way to do that and get that regression equation is simply by using a scatter plot. So the thing is, I need to change these variables around first because it uses height as the x or it uses the first column that you select as the x and the second column as the y. But I'm going to be predicting height based on shoe size, so I need those turned around. So I'm just going to copy this and put it over here, and shoe size, copy that and put it before it. So what that's going to do is this is going to be the x value and this is going to be the y value. If I just select those two and I go to Insert, Graph, I'm going to select a scatter type, and that will be this one here. And we see we get this scatter plot. And I'm going to add a chart element. So I go up to the corner here and we see Add Chart Element, and I want a trend line. And I want a linear trend line. What we see is that inputs that trend line in forms. So another thing I can do is I can select that line and I can format my trend line. And I can ask for a couple of different things. I can ask for the R squared value, which gives me the 0.8076, and I can display the equation on the chart. So now we've got the same equation from the regression that we saw is 50.141 plus 1.913 times x, which is shoe size. That's the x value down here. So what we see is we can get that regression equation and graph it quite easily by using Excel. Let's move on to JASP. Now, here we are with our correlation analysis that we did previously. Remember, our data is exactly the same. It's height and shoe size. And I'm just going to, instead of running a correlation, I'm going to run a linear regression. So if I do that now, and I'm going to select my dependent variable as height and shoe size based on is my covariate. We see I get the same values I had before. So H0 is the null hypothesis. The alternate hypothesis is H1, and that's 0.899. And R squared value is 0.808, which is the same as what we've seen previously. Our ANOVA gives us the same values we've seen before, 149 for our regression sum of squares, our mean squared value that gives our F ratio, and it gives us a calculation of our P. And finally, we see that we've got our unstandardized coefficients or beta coefficients, where intercept is going to be our height when shoe size is 0, and then increase with each increase in value of shoe size. So we could pick a few different options here for our models. We can provide some other different statistics if we want. You can go through these on your own and see what our different options are. One of them is giving plots as well, but these are residuals plots, so they're not really as intuitive as maybe the one that you see in Excel. Okay, finally, let's move on and do regression analysis in R. So we go back to R and open up our previous file that we've had, and we're going to use the same data frame that we had for the correlation. So that's this one, heights and shoe sizes. And we're actually going to use this exact same thing. We can get the correlations out, and then we can add in the regression analysis. So the command we're going to want to use is LM, and this basically means linear model. And all I need to do is tell it which variables I want. So linear model, it's basically these. Instead of correlate height in inches and shoe size, I'm going to height in inches, but instead of comma, we're going to use the tilde again. Remember I told you tilde basically means as a function of. So it's going to be creating a linear model of height in inches as a function of shoe size. Now remember last time again, we created a new model object that we saved our partial correlation test into. I'm going to do the same thing with our linear model. So I'm just going to call this reg.model. And I'm going to put it into that new object. And then what I'm going to do is I'm going to just see what reg.model will output. So let's run this whole thing again. So if I run that command, what we see is I get a new model called reg.model. It's an LM type. That's a linear model. And what we see is that it gave me our correlation coefficients, but now it gives me a linear model and it gives me my output coefficients, 50.141 and shoe size 1.913. That means as shoe size goes up, height increases by 1.913 inches. If I want to get a little bit more information out, I can add another command in here asking for a summary of that model, reg.model. Now, if I run this, I can run this command on its own, but I'll just run the whole thing again. And what we can see is it gives me the whole model here. It gives me some residuals information, but then it gives me information on the coefficients, my intercept coefficient and my increase with each increase in shoe size, and whether or not these are significant. And intercept says, is it significantly different than 0? And 50.14 obviously is. And is the slope 1.91 significantly different than 0 as well? And it says it is. It's 1.35 times 10 to the negative 8. Okay. So the last thing we can do is we can run a ANOVA on these values to get the output that we saw in SPSS. So reg.model. So now we can see that what's the benefit of saving our model into an object, because then we can run a summary and an ANOVA on the model object that makes life a little bit easier for us later on. So if I run that, see the last thing that we get is this increase. What we see is ANOVA. Shoe size gives me an F value of 83.955 and a P value of 1.35 times 10 to the negative 8. Of course, that's the same thing we saw back here. But the thing is, we have our F ratio that we saw in SPSS and the same one we saw in JASP, and that allows us to calculate the same things. All right, so go in and start doing this with the other data sets that I've given you. Start with RecordSales.sav or RecordSales.csv and try and run simple regression analysis on those. Pause here, run those analyses, and then afterwards, I'll give you the values that you should get in terms of your output for your beta coefficients and for your F ratio and P values for these different regression analyses. Okay, here we are back in SPSS, and we've got our file RecordSales.sav open. Now, I've got advertising budget and sales as my two variables that I've got. And when I ran the analysis, the output that I get looks like this. I get an R value of 0.578 and R square of 0.335. And now this suggests that 33.5% of the variance in record sales can be attributed to advertising budget. What we see is our coefficient is 134.140. So this is record sales in thousands. So you'd think the 134 $1,000 record sales if advertising budget was 0. And then we get an increase of 0.096 thousand with each increase in advertising dollars. So the next thing we see is our ANOVA shows that our F ratio is 99.587 with a highly significant value. So hopefully that gives you the answer that you were hoping for.